Good afternoon, everybody. I'm Sanjay Charitesh Makam from Rochester Institute of Technology, US. Our paper title is secRNNlong Malicious Code Classification using RNNs with LSTM and Transformers for Improved Cybersecurity. My colleagues are Aditya Sai, Hemanjali Villuri, and Pawan Mandip Reddy. They are from Vellore Institute of Technology, India. And our professor who guided us through this paper is Professor Naresh Shetty. He is also from Rochester Institute of Technology, US. I am going to present my paper today. You need to know why malware detection matters. Malwares are continuously evolving rapidly day by day. More than 560,000 malware samples are recognized every day, detected every day. Traditional antivirus tools fails because malware uses sophistication and polymorphism to this behavior. This motivates the need for AI-driven malware solutions systems that can identify unseen malwares fastly and rapidly. You can see graph on my right side which shows 2008 to 2024 how malware is evolving and how rapidly it is increasing day by day. And you can see 2008 is as low as zero and 2024's malware is like in millions. The problem and research have we identified is traditional ML limitations. Traditional machine learning algorithms work well for known patterns, but it doesn't work for the new daily evolving 560,000 malware patterns. And RNNs with LSTM's unit captures only sequential dependencies, but struggles to scale for the large scale malware detections. And transformers capture global context efficiency. So here our research aims to compare both architecture on a large real-world dataset and purpose a secure adaptive variant called secRNNlong. So here we discuss about the background and related work that we did. Here we summarize the existing approaches that are present in the market today. Prisma and OELSC explored classical and ensemble learning. Recent deep learning approaches detect new variants but often ignore sequential relations. Federated learning bring novelty but remain expensive or experimental. Hence, there's no still a unified deep learning framework balancing accuracy and efficiency. So we worked on that. So we used the EMBER 2018 dataset for doing this research. This dataset benchmarks for Windows malware detection, and this dataset includes over 1.1 million portable executable files. Both includes Benzene and malware files. Each file is represented by 2,381 features such as byte histograms, entropy, and header metadata. We also use Z-score normalization and an 80-20 split for training and validation. And this dataset has over 600K training samples and over 200K validation samples and 200K unlabeled samples. So this dataset is perfect for this research. So our proposed framework overview is this. So our proposed framework secRNNlong combines the strength of RNN and LSTM while improving the stability during training. It captures temporal dependencies in static features and used modified LSTM gates for robust gradient flow. So we benchmarked it against the models vanilla RNN, LSTM, BiLSTM, and GRU. Coming to transformer architecture, we also implemented a transformer architecture adapter for static malware data. Each of these has 2,381 features is treated as a token. Using multi-head self-attention and positional encoding, the model learns global feature relationships in parallel, achieving high scalability. So here you see input projection, each has 2,381 features treated as tokens. Multi-head attention, 8 attention heads across 4 layers, which enables parallel processing and global feature relationships. Multi-head attention. This is the key to our comparative analysis. So here we see RNN and LSTM model results. Our top performance, which is our variant secRNNlong, achieves 90.8% accuracy with 0.92 precision and 0.93 recall value. So here the chart shows model performance comparison. So you can see vanilla RNN's accuracy is 90.9 and LSTM's accuracy is 90.8 and GRU accuracy is 90.95 and our variant secRNNlong is 90.8, which is almost as vanilla RNN. And we have consistency results all over the RNN variants, which maintains ROC AUC of 0.96 across EMBER 2018 dataset. And next, coming to transformer results. So transformer architecture demonstrates superior in generalization, which has achieved 91.2% validation accuracy on EMBER 2018 dataset. And also it is higher than the RNN LSTM models, which achieves only 90.8%, and the transformers achieved over 91.2% validation accuracy, which emphasizes no overfitting trend. And here you can see training and validation curve shows smooth learning confirming strong generalization while using transformers training process. So here comes the comparison between transformers versus secRNNlong. So when we compare both models, transformers shows slightly higher accuracy and generalization, while secRNNlong offers faster training and lighter inference. On both the EMBER and BODMAS datasets, results remained consistent in transformers. So you can see accuracy in transformers is 91.2%, and in RNN's secRNNlong variant that we highlighted has only 90.8%. And you can see the training time for secRNNlong, it's only 0.8, which is faster than the transformers. And you can see inference speed, which is lower than the secRNNlong. So inference is good in transformers, and memory usage is good in secRNNlong, which uses only 1, and transformers is 1.3. And overall, I wish to conclude that is transformers has better generalization. You can see that 91.2 accuracy, and secRNNlong is faster training and lighter inference. Both achieves greater than 90% accuracy and EMBER 2018 dataset. Hybrid approach viable for real-time deployment. So our next slide is key insights and discussions. So to summarize the highlights or insights, RNN LSTM models are great for sequential patterns, which we already discussed. Transformers handle global relationships and unseen malware better, and it has better generalization as well. Combining both could yield real-time scalable detection in enterprise cybersecurity. So you can also see that RNN LSTM's better works for known malware patterns, and it has lower computational requirements, and it has faster inference for real-time systems, whereas Transformers has parallel processing capabilities, and it is better generalization compared to the RNN LSTM, and it is superior handling of complex relationships. So our research finding says that both has distinct advantages for both architectures in malware detection applications. And also coming to performance balance, it has trade-offs between accuracy and computational efficiency. And here we discuss about conclusion and future scope. Key conclusion: both models have achieved greater than 90% of accuracy and EMBER 2018 dataset, which shows Transformers has better generalization than RNN LSTM variants, and RNN LSTM offers deployment advantages. And coming to our future work directions, we are planning to integrate AI copilots for SOC analysts, building multi-model detectors combining static and dynamic features, and exploring self-supervised pre-training or unlabeled executables. Together, these approaches bridges deep learning and cybersecurity for smarter threat defense. These are the primary references that I would like to mention, and these help so much while doing our research, which is EMBER 2018 dataset from Anderson, and it has over 1.1 million PEs for Windows malware detections. And for transformer architecture, we use Vaswani, Attention is All You Need Pepper. And for malware detection, we used Colosana, Jaji, B, and others for malware classifications with recurrent neural networks. So this is what I would like to say about our paper. If you have any questions, you can address me to my email sanjaychariteshmakam@gmail.com. And I would like to specially thank my professor Naresh Shetri, who continuously supported us and guided us throughout this paper. And I would also like to thank ACM SIGCITE 2025 organizers. So thanks everybody for listening, and we appreciate your engagement with me. So you can address questions to my email. Thank you.